Oh, I should set my stream caption. Out the chat. Since I upload these VODs to YouTube, so this stream is going to be more about reading about the virtual memory management side of things, finishing off the virtual memory manager, getting to a point where I can map pages from kernel's physical memory allocator. And that's quite a big goal, I think, for tonight. So we'll stick with that. Let's see what's on the playlist. This won't be in the video on YouTube, so copyright stuff, you know. Do 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 do. Okay. Right, I need a reference to the XV6 OS here. And this is the SDM. Because we'll be covering the last couple of pages, I think, in the paging chapter. Task management, interrupt protection, paging, here we go. So we finished like this section 4.5. I don't know whether we probably need to read about access rights on 4.6 and then I'm not sure if I need to pay any attention to this caching section, because funny enough, I've not seen that in any open source OSs, which is strange. So I wonder if it's an optional feature. Maybe. Yeah, I think everything else after that is just different concepts that are not really related to the memory stuff. So mapping segments to pages. Let's just flip this to lo-fi, I think. A bit more neutral to my ears. All right. So, um, I think I'm going to get rid of this. I don't want to convert the address. Yeah, let's keep this as like a physical thing because I think the use of it will be needed to pass to other registers. So we've decided not to put any support in for 1 gig or 2 meg pages yet because we don't know enough to handle those. Now, one thing I need to understand, so from a client side, if I cast my mind back to the NVMe driver, so we get a memory location of where a bunch of memory mapped IO stuff is going on, and what we can do with that is map it into our VM, which I'm not even sure what the client side view of this would look like. Hmm. Do, 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 do. I wonder if this source code has got an NVMe driver in it. Make file system might be in here. Disk layout stuff. File socket stuff. Can we find I append need to be signed in. Pull this one up. So I kind of want to see what about he might be a bit difficult to search on. Holy crap, is that an implementation of grep? Oh, simple grep only supports those 4 operators. Well, I guess it works. That's kind of like the majority of grep usage. File alloc. What about this? Pipe sys file. Maybe in here. I think we're at kind of an abstraction layer. fd alloc, I guess, is a file descriptor. File close f. Why did f get created? That's a struct. File alloc. Acquire a table lock. ft, what are you? A spin lock and a file array. Device functions read write. Memory copy of an inode, file node, pipe maybe. Just have a quick scan down its source code file names. Maybe I can spot it from there. Could it be an FS maybe? Superblocks. File system implementation, 5 layers, blocks, allocated for raw disk blocks, log, crash recovery, inode allocator, reading, writing metadata, directory inode with special constants. Zero block, allocate 0 disk block, bread, right, bio. What's B get? Mem ID. Oh, ID. Here we are. see any comments here. Simple PIO based non-DMA IDE driver code. Okay. We found the specifics. Let's see on the initialization IOA pick stuff, init lock port stuff. Yeah, this is definitely IDE driver stuff here with sectors and all right, and then the setting up interrupts. And it looks like it has a queuing mechanism. What about memID? What's this doing? Fake IDE disk stores blocks in memory. Useful for running kernel without scratch disk. Okay. Nothing really useful. I guess I'm gonna have to just try and have a search for this map pages. No one's using it, really. Second it, what page directory? Create page table entries for virtual addresses starting at VA. Might not be page aligned. Okay. Looks like we're in a rabbit hole, and part of the challenge is unraveling ourselves. Keymap, set up KVM. Sets up the kernel part of a page table. Map pages here, physical and physical start. Page directory, page table. Kalloc returns. Let's just go check this out. Okay, one page of physical memory returns a pointer that the kernel can use, returns there if the memory can't be allocated. Okay, standard. So why What is this guy? Oh, it's a uint. Okay. It's just so weird to read that being casted as a PDE, which is a page directory entry, when this returned a memory address. So it blanks the page. P2V is the physical to virtual macro, I believe. Let's go have a look. Kern base. So if you're going from physical to virtual, you are adding on this first kernel virtual address. And if you're going from virtual to physical, you're negating the kernel base. Hard to envision what they're mapping there because I don't know what their memory layout. Like I don't understand why it begins at that hard-coded address. So I'll carry that as an assumption for now. So map pages. What is K? K map. Kernel map. Initialized here. And that weirdly looks like it's just some custom struct. This is not needed for set up KVM and exec, set up every page table like this, not kern base, user memory, text data stack heap. Map to physical memory allocated by the kernel. Kern base, extended mem. That's for IO. The kernel allocates physical memory for its heap and for user memory between v2p end and the end of physical memory, directly accessible from end. God, this is just horribly hard to understand. Not very clear. So we just have a bunch of a pointer to something called vert. which is an address. What's this data? Defined by kernel.ld. External. Kernel.ld. What are you doing? It's a linker script for the JOS kernel. So that's been placed at a very specific place in memory. Include debug information. Not a lot really going there, other than some section definitions. All right. And it's using physical locations in this struct. Physical start and end, and then permissions flag. So for each one of those items that it defined in the K-map, it's mapping pages in the VM. Where's my pen? Okay. Yeah, this is a bit tough. Mapping page directory. Does that change? That's not in the for loop. So it allocates one page 4096 bytes, and it's just running this. If it fails, it frees returns 0. So what's map page is doing? It sounds pretty important now. Creates page table entries for virtual addresses starting at VA. VA. Let's go back one. KVirt. So it's these virtual addresses that it's got from these constants. Doesn't make sense how you can define a virtual address like that. It's kind of like the problem in my head is it's a bit of a chicken and egg scenario. Like nothing exists in your virtual memory map until you put it there. So why does it have these hard-coded virtual addresses? So page dir is the page that it got from the physical allocator. This VA is just a virtual address. So creates a page table entry for virtual addresses starting at VA that refer to the physical addresses starting at PA. So the next two params are size and physical address. So it gets those from the map and oh, it's kind of making a little sense now. See, 0 to extended memory, so kern link, which is what's set up through the assembly file. What's this phy stop? Why is it this value? Top of physical memory. Sounds like just some hard-coded stuff for the fun of it. Might be a bad example. Like, for example, we are handed to us the memory pages or the memory layout from the bootloader. We don't know how much RAM there is, or we assume we don't know how much there is of RAM, and we pass it on the kernel load. So at the beginning of our journey, we know where the physical memory is and how much of it that we have. Where this is kind of like, I don't know, it's kind of taken a bit more of a simpler solution maybe. Maybe it's got its own bootloader and it's not as elaborate as Lamini. Okay, so let's try and go through it then. So then that's just a size calculation. And then there's this physical start location. And the permission flag. So A is page round down from the virtual address. So that page aligns it, 4096, I believe. Page size 4096. Okay. That gets the rounded down of the size that you want. All right, let's begin for loop. It walks from PGDIR, which is the physical location from the physical memory manager. That is a bit wild. Returns the address of the page table entry and page table PGDR that corresponds to virtual address. Thank you for that follow, Crollo. So, given the physical location from the PM and a virtual address and an allocation flag, what's PDX doing? PDX shift. Offset of the PDX in a linear address 22. That sounds familiar. Let me just go check my macros. Yeah, that's the shift for grabbing the page entry indexes. Okay. If the page entry is present, then set this variable. It makes no sense at all. AGB, what's up, buddy? How's it going, man? Yeah, I'm not too bad, dude. I feel like I'm in the hardest difficulty. Like we've got to a point where we've finished this walking of a virtual address. But as far as thinking about the theory of creating a virtual address is a bit mind-blowing right now. Because I need to ask Discord, to be honest. I need to have this conversation in OS Dev. It's confusing the crap out of me. What tracks? Because what's wild to think is that if you're in the kernel, or if you're client program running in the operating system, and you've written a program, and that program says declare 4 bytes for this variable, declare 4 bytes for this variable, and declare 4 bytes for this other variable. So you've taken 12 bytes of RAM. Well, yeah, 12 bytes. But each one of those variables that you have in that code have got different memory addresses. And they're all actually physically in the same page of memory. What tracks what parts of a page I've got to I need to turn this into the right question. So So if a client program in your OS is a program that declares 3 variables in code, each variable is 4 bytes in size. During that allocation, one page in the PM deep in the kernel is allocated, correct? And if so, who is tracking what parts of that one page is free taken? Because everything about all the memory managers and all the code that I'm seeing is you track pages. You don't track individual bytes within a page. Someone's going to say, you need to write that management. I can't see any other way around it, really. Like, I bet that is something that has to live in the kernel. Yeah, it's one thing about the virtual memory stuff, or like the virtual memory paging is all about just creating virtual views on the physical memory. But those two things are not a full realization of managing your memory. So like at the moment my OS says I want to allocate memory, and it says here's a page of memory for you, 4096 bytes. And now something has to go, well, okay, I only need 4 bytes, and this other part of the kernel needs 8 bytes and this other part needs 32 bytes, so we can all share the same page. And even the VM doesn't answer that question. So the VM allows you to declare a variable, an address, a very physical, specific address in virtual memory, which, yes, does map to a single page table entry. Like, because you can divide that address by 4096 and bam, you've got the index. And the offset, that's carried in the virtual address. I really should put the layout of virtual address from the manual. In code, just for... I think someone can answer this because I'm confused as hell. Someone's going to go, yeah, you need to write this as another module alongside the VM and the PM. And we're like, no! Excuse my squeaky chair. I don't know if it is squeaky. Yeah, whilst I'm waiting for someone to hopefully answer that question, let me grab the layout of that virtual address space, which will be chapter 4. Paging structure, caches. Weird. Is it in here? I think that's it. How am I going to represent this in a code comment? HTML4. Page directory. Page table. him off or PDPT. And then the page directory, then the page table. And then the offset. So let's do 47 to 39. And this one's 38 to 30. This one is 29 to 21. Kind of make these a bit wider. It's a bit hacky, but it's whatever. This one's 22, 12, and this guy 11 to 0. Given that it's a Saturday night, I doubt anybody's going to be around. Linux has this concept. See if I can Google it. Called the slab allocator. The general purpose allocator is described as a slab allocator, which is very similar in respects to the general kernel allocator used in Solaris. It's very heavily based on the first slab allocator paper by Bonwick. So let's just have an overview of what this is doing. The basic idea behind the slab allocator is to have caches of commonly used objects kept in an initialized state available for use by the kernel. Without an object-based allocator, the kernel will spend much of its time allocating, initializing, and freeing the same object. The slab allocator aims to cache the freed object so that the basic structure is preserved between uses. Consists of a variable number of caches that are linked together on a doubly linked circular list called a cache chain. A cache in the context of the slab allocator is a manager for a number of objects of a particular type. The caches are linked via the next field in the cache struct. Okay, it's fine. Each cache maintains blocks of contiguous pages in memory called slabs, which are carved up into small chunks. For the data structures and objects the cache manages. The relationship between these different structures is illustrated. So I'm assuming object here is a variable. The allocation of small blocks of memory to help eliminate internal fragmentation that would otherwise be caused by the buddy system. System doesn't waste time allocating, initializing, destroying objects. Benchmarks on Solaris showed excellent speed improvements for allocations of the sub-allocator. The better utilization of hardware cache by aligning objects to the L1 or L2 caches. So this doesn't sound like the problem that I have in my mind. Um, yeah, so this just sounds like it's trying to optimize fragmentation and reuse of memory areas. Which sounds great. It's an optimization. It's not the problem that I'm looking for, or the problem that I've got in my head. So in this answer, malloc happens in user space. That would go in the heap, which malloc may request a new page if it runs out. 4 times 3 bytes would place inside a single page. What is tracking that? A lib inside. It's got to be like the C standard library, I'm sure. As in, it's the source code under malloc, I think. I guess it's the source under malloc. I mean, I could go find it, I guess. It's almost like a memory manager, but even a C program on Windows or Linux doesn't have memory management per se. And when you call malloc and free, there's something tracking what parts of the heap you're allocating and freeing. Malloc tracks how many pages it's been given and requests more when it needs it via a syscall. I think a map is the syscall usually. Let me just make sure I got this question correct. So if there's lots of malloc and free calls, um, Yeah, I think I understand. Like, you could have a bunch of mallocs, and then you could have things that are freeing up data from earlier in the page, but they're not necessarily suitable for a future malloc because it's bigger. And it's kind of like the problem of having a chunk of memory and it becomes fragmented. And at some point, you're going to want to shift memory around, or yeah, many ways to do malloc, but a good one will try to reduce fragmentation. I'm trying to. Uh, do I need to solve this problem in kernel memory? I don't think I do. I don't think. I need to. Well, do I? I do need to solve this even at the kernel level because device drivers. It doesn't so much track how fragmented the page is as much as it just tracks which bits are free and which aren't. Which you can use to figure out how fragmented it is. I mean, without defragmenting logic, it will become fragmented. Like, if you're not spending time moving memory within a page back down the page to where memory has been freed, and therefore compacting the memory boundary or the memory chunk, it's forever going to be fragmented. Vague. The heap is a range of memory in virtual address space. Malloc returns memory from that. It may not know about pages at all. The heap is a range of memory in virtual address space. It may not know about pages. Why wouldn't it not know about pages? The global variable is the linker, of course, otherwise you'll use a space memory allocator. That memory allocator. I think I'm trying to write a malloc in the kernel. Don't yet see how this works with the VM-PM. You always end up with some sort of allocator in the kernel, right? So that kind of answers my initial problem, but I think what he means by that is I don't think it's as important in kernel space, because in kernel space everything's a bit more finite. Slab is good, or just slob to start with the simple thing. Start with bump. All right, we've got 3 things to look at there. So we've got bump, slob, and slab. Right, let's have a Google then. This might answer some questions. It might straight away be like, ah, yes, this is what I want. Bump allocation is a fast but limited approach to allocation. We have a chunk of memory. We maintain a pointer within that memory. Whenever we allocate an object, we do a quick check that we have enough capacity left in the chunk to allocate the object, and then update the pointer by the object size. I'm guessing this is not a defragmenting that is not a deallocating algorithm, which is why it's simple. It's just a forward-only implementation. Bump is very simple. You will have to change it. Yeah, I think that's Hello World. Slob is very simple. You can keep it for a long time. And slab is a bit more complex, nearly modern. So each slab has some pages that it then splits up, and it hands the split regions to the user. When the user, oh, okay, let me think about that. Holy shit. So each slab has some pages that it splits up, and it hands the split regions to the user. When the user frees one of those regions, it does an intrusive linked list of all the free regions. So when the user tries to allocate again, it can go directly pop it off the list of free regions. Oh, I see. Oh, I see. Save pmem alex. And that was the whole point of that document we were reading earlier about what the slab was solving, the problem that it was solving. Uh, they all do that. It's really a naive allocator that can be very fast due to the tiny amount of housekeeping involved, but you have to live with a pretty heavy constraint. There's no free operation. You just destroy the whole thing. This means that the program's data space just grows up for each request, and trying to freeze something doesn't make any sense because you just put a hole in the address space. Well, there's probably some funky VM stuff that would work, but that gets complicated. Um, all high-performance allocators today are just minor versions of it. For example, make all of this thread local to avoid locking. Leia! Hello, hello, hello. You are my... Oh my god, you've even gifted a sub to GB. Holy crap, you are so nice. Thank you so much. That's wild. I'd never thought I'd get subscribers, but here we are. Thank you for that, Leia. That's super cool. I probably need to pay somebody to make me some sub icons now. Leia is one of my Twitter followers, GB. She's one of my most supportive Twitter followers, I should say. So thank you, Leia. Or you can go the classic first for allocator, slob, simple list blocks. Okay, so we've got some cool stuff to work on now. We've got direction. The hardest and horriblest thing yeah, the most worst thing about OS dev is getting to a point where you feel like you don't have direction and you're like stuck in a hole. This is why it's kind of an insane domain that you need mentors and community. Like if it wasn't for this OS dev community, I don't think I would survive. Oh, slob actually stands for the simple list of blocks. Interesting. Let's make note of that keyword too. So a first fit allocator sounds like it's got some other algorithms that we can pick on. So I'm going to put this as a document in the Git repo actually, because people will appreciate what these things are if I start coding them in the kernel. Like, what is it? Right, it's a memory allocator. And then what's a memory allocator? Why do we need one? And I can explain that too. Um, okay, cool. We've got homework. Sorry, Leia, how are you doing? How's your Saturday going? Do 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 do. Hope the music's not too loud, by the way. I'm not sure how what the volume like is coming through on OBS. Um, Saturday's going good. Had it chill today. Music is good. How's your weekend been so far? It's honestly, it's been quite a low energy weekend. So I'm a bit below my usual average energy levels. It's a side effect of a very busy week. So work was pretty intense this week, and it always leaves me a bit brain fried. Um, Honestly, I'm quite surprised that I decided to stream tonight because I didn't think I would be up for it, but it's actually an easy night. I'm just doing a bit of research into some problems, doing some planning. Um, but you know, if you need to ask any questions or you'd like to know anything, uh, please feel free to ask because I love talking about anything really. I'm just gonna go grab um, a new water. I've run out of water, so I'll be back in just a minute. Okay. Okie dokie. You can relate. Yeah, I've seen some of your tweets from the past few weeks. It doesn't sound like your usual self, or you're going through some things, and I hope everything is good and improving. Um, Allow me to be a happy distraction for you. Yeah, no problem. There's only been one uh, stream since coming back from 6 months ago, and that was Thursday night. It is on YouTube. It's a 3 hour video, but there's not much isn't as much happening in that stream other than me welcoming everybody back. And you went through a lot. Oh, okay. Time heals all wounds, so to speak. I'm moving house in about a month's time. I've probably not said anything, and I probably won't announce this on Twitter either, because I've only been in this house like 11 months, but I'm already moving. I have to restart. Do I like my ass all over again? Oh shit! Why? Why have you restarted, GB? Yeah, there's the main reason is this house was kind of like the first house to get me onto the housing market, so it wasn't the ideal house or location that I wanted to live. And then a really, really nice house came up because I was keeping an eye on the housing market, and a new house came up, and I was like, oh my god, that's an amazing place that I want to live in. It's a beautiful house. Now that's the house that I want to live in, right? And then I didn't think I could get it, and I rang my mortgage advisor and my advisors and said, like, can I buy this house? It's a lot more expensive than the one I'm in now. I can afford it, but I don't know if I have the collateral enough, loan to value to be able to get it. And it just so happened that I was like perfectly aligned to be able to bump up my purchase power just from the 11 months that I've been in this house. So yeah, I put this house up for sale and it's sold within 2 weeks. And then I put an offer on the house that I want, and they took it straight away, which is amazing. And then it's all in motion. And I think in about 6 weeks from now, I should be moved. And I think one of the biggest things that I'm looking forward to is I so miss my piano. And I don't have the room in this house to put up the piano at all. There's no room for it. And when I move, I finally am able to put up my piano, and I've got a much bigger room for my computer setup, and half of the room can be for my music equipment and my piano, and I'll be back to playing the piano, which will be amazing. So I can't wait for that. Oh. Way too many issues with it, and you gained a lot more knowledge, so it made sense to start over. That's brilliant, GB. Yeah, like I imagine even with this OS that I'm doing now, I'm sensing how it's deteriorating the longer I'm doing it for, just because of the more things that I'm finding out. So I'm just going by gut feel that as soon as the value to effort drops off, then I might start another one. Who knows? Like I would love to. I know people say not to, like don't write a bootloader, but I'd like to just create something super simple and specific to a need, just to get the experience of loading, like understanding how to do a handoff from the BIOS to the kernel, doing things like the kernel load, putting that into memory, lots of stuff that I just wish I had a bit more knowledge on. And using a bootloader kind of took that away from me, and I'm still on catch up. Yeah, it's a pretty amazing feeling, Leia. I drove past the house again, or the new house, a couple of days ago in the week, just to check it out. And as soon as I like drive into the street, I couldn't believe that was the house I was buying. Like this, it was genuine excitement this time. I'm like, oh, this is a house that I want to live in, as opposed to just a house to get me on the housing market. Do, 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 do. It feels so amazing to think that I've got subs. I'm now like feeling like I'm a proper streamer and I have commitments to keep up now. Um, Let me know if you guys get ads, by the way. I need to somehow disable them or just turn them off. All right, let's have a nosy at this slob allocator. Let's try Wikipedia. So, slob is a simple list of blocks allocator. It was one of the 3 available memory allocators in the Linux kernel up to version 6.3. The other 2 are slab and slub. As subscribers, you don't get ads. Oh, win-win. Nice. My main Twitch account pays for Twitch Turbo, which it's that old hacky way of paying Twitch to not get any ads on any stream ever. That they don't advertise. But there's something legally binding that they can't take the product away. Yeah, so I wasn't sure what it was like for just a raw sub on a channel. Okay, so the slob allocator is designed to require little memory for the implementation and housekeeping for use in small systems such as embedded systems. Unfortunately, a major limitation of the slob allocator is that it suffers greatly from external fragmentation. And this is again a problem in the back of my mind all the time, is that memory allocation seems like you want to housekeep the fragmentation of the memory chunks, or else you're going to get an operating system that is just, it could get to a point where it's so fragmented that it will tell you that it doesn't have any memory to give to a program, and the only way to solve it is by restarting the computer to nuke the RAM. Or you would have a garbage collection routine that would have to pause every application in the machine. Like the entire machine would stop for a number of seconds whilst the kernel sorted out the fragmentation of memory, which is pretty awful. But what's good is that for our kernel, we don't even have an interface yet to declare like a memory allocation for a number of bytes. And even if we get a hello world one, we can keep implementing a better algorithm underneath that function as our knowledge increases, right? So an example that I'm trying to paint is in the memory module that we have. We have this calloc, which is like malloc, but it's kernel allocation. And you pass that a number of bytes that you want it to allocate, and it allocates you a number of pages based on that amount. But it will always allocate you a page. Is the problem, is it doesn't share pages with anybody. And we need a malloc that will share pages. So Slob currently uses a first fit algorithm, which uses a first available memory, available space for memory. So algorithm 1 is a forward only pointer with no freeing, and this algorithm is first fit, so I'm guessing it starts from the beginning, looking for a suitable slot for your allocation. Best fit finds the smallest space which fits the required amount available, avoiding loss of performance, both by fragmentation and consolidation of memory. Oh, I'm getting flashbacks of a memory allocation concept where if this was your memory base and you had some chunks allocated here, right? So if I put an X to say this is allocated, 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 allocated. Now, if you delete that X and free that chunk up, pretend it's 32 bytes. There's a 32 byte chunk of memory that is now available for allocation. Now, if somebody comes along and frees this X up, this X says, okay, I'm 32 bytes, right? But it quickly checks its neighbors and says, can I merge with another free block to my left or my right? And it'll go, oh, this guy's free. So it removes that wall and it just says, here's a 64 byte chunk. And you've kind of like defragmented memory because you've now consolidated that memory chunk. And if this was to free up and this was 32 bytes, then this would now merge and this would become 96 bytes. So then if somebody comes along and says, I need 32 bytes, well, it doesn't have to go to the end here and forward allocate more pages. It can come back here and go, we've got a nice big chunky 96 byte slot for you here, so you can have your 32 bytes. And then this becomes 64 bytes 3. So get this kind of scenario. And it's kind of a nice way of keeping the memory defragged. I wonder if we're going to see that in the slab, or the slub, should I say. Okay. So it was back in 2008, a reply from Linus. He suggested the use of a best fit algorithm which tries to find a memory block which suits needs best. Best fit finds the smallest space which fits the required amount available, avoiding loss of performance, blah, blah, blah. By default, the Linux kernel used a slab allocation system until version 2.623, when slub allocation became the default. When the config slab flag is disabled, the kernel falls back to using the slob allocator. The slob allocator was used in DS Linux on the Nintendo DS handheld console. Interesting. So can we at least see some pseudocode? Implementation. Oh, that's slab. No, I want... No. Let's go back to Google. Let's try. Oh, this looks like a presentation. Let's see if we can find a slub.c file. Slub allocator. What project is this? Fusion? Cop? What? No idea what it is. But it is C code. A lot of documentation here, which is nice. We modified the slub to implement a best fit algorithm. We added a slub best fit alg definition. The slub will use the best fit algorithm. If it's not defined, the slub will use first fit. So there's best fit and first fit. Write that down so I can explain this later to other people. We modified the slab allocator to define the best fit page. We modified the slab, blah, 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 blah. How slab works. The core of slab is a traditional K&R style heap allocator. Support for returning aligned objects. The granularity of the allocator is as little as 2 bytes. Wow. However, typically most architectures will require 4 bytes on 32-bit and 8 bytes on 64-bit. The slub heap is a set of linked list of pages from alloc pages, being the page allocator, the PM. And with each page, there is a singly linked list of free blocks, slub T. The heap is grown on demand. To reduce fragmentation, heap pages are segregated into 3 lists, with objects less than 256 bytes, objects less than 1024 bytes, and all other objects. Allocation from the heap involves first searching for a page with sufficient free blocks using a next fit-like approach, followed by a first fit scan of the page. The allocation inserts objects back into the free list in address order. So this is effectively an address ordered first fit. Okay. Above this is an implementation of kmalloc and kfree. Blocks returned from kmalloc are appended with a 4-byte header with the kmalloc size. If kmalloc is asked for objects of page size or larger, it calls alloc pages directly, allocating compound pages so the page order doesn't have to be separately tracked, and also stores the exact allocation in page private, so blah, blah, blah. Okay. Slab is emulated on top of slab by simply calling constructors and destructors for every slab allocation. How much code are we talking here? Let's just get a good feel to how much code this is demanding that we know. It seems quite a lot for what it was describing, but let's have a nosy. Seems to be well documented. I like this. Restruct page fails to manage slab allocation aspects. How to avoid horrible messing in lines and turns. We'll just define a restructation. They just look like some double dispatch kind of functions. Spin locks. Set slab. Encode the given size and next info into a free slab block S. Okay, this is just doing the linked list stuff, I believe. Okay, so it's kind of put my mind at rest about thinking about we did need something more than just the VM and the PM. So to start really simple and dumb, I guess, at the beginning is that we could just do a first fit allocator. Like I've got the theory in my mind to do that without even reading other people's code to just set that metadata up. But ideally, we want something with a malloc and a free, because I want to get the interfaces for be able to start a user space program in the future, and I can keep this like noob algorithm for a while we get rolling. So it's quite. What's really nice now is that we've got a lot of options, and they're all nice options too. Like there's nothing terrible here, like or scary or difficult even. It's just a bit of a learning curve, and just the time spent implementing it. But it's going to be fun. Actually, it's going to be satisfying knowing that we're conforming to the malloc and the free interfaces. So I'm excited for that. What I don't want to read this code. I want to find someone's maybe Stack Overflow. Oh. Slub resources. What's funny is I keep seeing links into the Linux kernel. I mean, should we just have a nosy to see if it's readable? How much code are we talking in here? Not a lot. This was 03. Wait, this is the Linux documentation that we were reading before. What is KNR? Oh, it's a documented algorithm. I think what's really cool about this is it's kind of like prompting my thoughts about how garbage collection works. Maybe. Okay, so conceptually, the slob has three lists of object tracking, small, medium, and large. That just seems to be a core part of the algorithm. Oh, is it on Wikipedia? K&R wrote the Bible on C. Oh. Hi, Marion. How you doing? Good to see you again. I've just come to the realization that OS Dev is such an emotional roller coaster. And I don't know if you guys feel this too. Like one day you can feel absolutely excited and full of energy about knowing exactly what you're doing, how to solve a specific problem, and it's all like blue skies, happy, happy, right? And then immediately in the next hour, you find yourself in a immense rabbit hole of I don't know what the hell I'm doing. This is confusing, overwhelming. I'm not going to be able to do this. I should quit. And then the next hour, you're free again. Like I used to have this feeling when I was a junior, when I was like 12 years old. Like never in my normal career do I get this at work or anything, right? But OS dev is so complicated. Like it's so hard to find out how things are done that it gives me this roller coaster of emotions all the time. And I'm almost feeling like you need to be a bit of what's the word for it? A masochist? You know, the whatever the word is that you like to inflict pain on yourself. That word. Um, you can totally relate. Good. Yeah, because I'm going through that all the time. Like even for streaming, by the way. So I want to turn my stream on and share with people what I'm currently doing in my OS, but I'm like, if I don't have a clear plan about what it is I'm doing, why should I turn the stream on and show people that I'm in this state of, confusion? Uh, and that's what stops me from streaming sometimes. So like I'll spend days working on the OS, but I won't stream it because I'm like, there's no way I can stream just sitting here flipping between the SDM and Googling things and having Discord conversations. What's your day job, Marion? Are you in OS dev as a day job, or are you a hobbyist OS coder like me and you do something else? Bootstrapping the stream? Yeah, true. There's some game developers on Twitch that I watch though, and they're so good at just turning their stream on every day, regardless of what state they're in with their projects. And they can turn their stream on those days and like on a Monday, and they'll go, I'm just literally going to write in a Word document today because I don't know what I'm doing and I need to plan the week. And I'm like, God, I wish I could be like that. Marion, you've subbed. Oh my God. I have 3 subscribers. This is incredible. Sorry, Leia's gifted the sub. Sorry, Leia, you are crazy. You've gifted 2 subs. That's so cool. Um, you don't mind me posting a tweet and tagging you, do you, Leia, after stream? I could not do that if you prefer. Um, I fix stuff usually it's user error, but tend to breakers, sensors, and transducers. Also, do you do embedded programming? That sounds really cool. For my day job, I know you didn't ask, but I'm going to tell you anyway. I don't do hardly any coding anymore. So I took on a technical lead role about 4 years ago, and I didn't realize how little code that role entails. It is hardware stuff. Cool. A lot of the devs that I work with have always been business developers, so uh, they're always in the CRUD business logic domain and using like databases and web apps and stuff like that. And every single one of them like looks upon people that do embedded programming as like the gods of the computing world. Like if you know how to write drivers or talk to hardware, it's like elite. So it's been pretty mind blowing for them to hear that I'm working on an OS. My trader got to learn automation at school. Cool. Um, hmm. All right. So PC is just a layer. Okay. Operating systems may use different slab sizes and internal layouts depending on the size of the objects to be stored. The reason for the large slabs having a different layout from the small slabs is that it allows large slabs to pack together into page size units, which helps with fragmentation. For example, objects that are at least an eighth of the page size for a given machine may benefit from a large slab size, explicit free lists, while smaller objects may use a small slab setup, embed the free list tracking. Bonwick's original presentation of the slab allocator already made the distinction of layouts for large and small slabs. Oh, that's the latest allocator that Linux uses, the flub. I'm just um I just had a thread spawn in my brain just now about just detaching myself from the theory and getting together my own algorithm that I can think about to create the malloc and the free. The problem, I'm going to actually know, I'm going to read a bit more implementation details because I want to know how people are storing the metadata. I mean, how would I store the metadata? So if I'm writing a malloc, where am I storing the metadata around the page that I'm administrating? Because that's the cost, right? But I could put that cost on each allocation. So I could just say, like, I don't know, 1 byte before this allocation is always going to be the metadata byte. And I can manipulate the bits in that byte to understand what I need on that allocation. All I'd need was 12 bits per page, right? 12 bits. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 decimal, yeah, 1 page in size. Um, hmm. Let's just check this code. So 3 lists. Uh, Slub next. Return the next free slub pointer after this one. Slub last. Slub free pages. Slub page alloc. Page size align. Allocate a slub block within a given slub page. Need to fragment the head to align. Exact fit. Unlink. If previous set slub free list. Fragment. Entry point into the slub allocator. So this is the main algorithm. Iterate through each partially free page, try to find room. Improve fragment distribution and reduce our average search time by starting our net search here. So that's just a saved pointer of where it last allocated. Which is a common behavior I've seen in searches and allocation searches. Not enough space, must allocate a new page, and I'm guessing it's going off to spin lock IRQ, virtual to page, set page slabs, load new pages. So this is the point where it's doing actual memory allocation with the kmalloc. Well, this is all the physical actually. This is all when it just wants to allocate physical memory for the slob stuff. Um, whomever wrote this knew someone else who's going to read it, actually making a ref of the book. I find that the Linux kernel has some really funny documentation. I don't know if you mentioned you've done the HPET before in a last stream, and I don't know if you've ever checked the HPET timer code in Linux, but some very grumpy devs in that source code, understandably for how buggy the HPET timer is. But yeah, the code comments are horrendous in a funny way. I've never heard of this K&R before today. So it's not too much to digest here, which is nice, right? It's about 400 lines of code. It would be nice to find some source on the internet, some academic representation of this allocator, instead of just that. This is the best source we have right now, or have found. I guess we could ask ChatGPT. It might have some knowledge. We could definitely try that. Small implementation in C of a slab allocator in user space. And we want slob. Basic memory allocators explained in 10 minutes. What is this? Ooh. Bump, body, slab, free list. Don't believe anything you read on Google about OS resources and other bullshit. A slab allocator is literally just a fucking array with a singly linked list pointing at the next free item. Okay. Sounds like someone's had some frustration of how this is being described. And they're like, dude. It reminds me of when dependency injection was big in Java and .NET times. And there was some joking t-shirt that was like, I thought I was getting a dependency injection certificate and all I got was a constructor parameter or something. It was some funny explanation of dependency injection at the time. That is, slab allocators are meant to give you single elements of one size, which often means they're used for one specific type of item. They're very fast and efficient, and unlike a bump allocator, they can free items, but do need to maintain a linked list and are limited by a single size of allocation for a single item. You can fancy these up by creating an additional linked list that points at multiple buffers rather than using a single buffer, so you can dynamically grow and shrink the amount of memory the allocator is using. So the allocator will probably just... Will it have a determined size for how big your RAM is? I guess it doesn't matter. Like, they can start very lightweight and your array of metadata can grow as needed. You can make that a self-resizing object. A free list allocator, by far the most complex. A free list takes a region of memory and divides it up by chunks that fit the requested allocations, keeping a linked list of free chunks, hence the name. That it only has to search that list to find a chunk that fits when allocating. When previously allocated chunks are free, they're merged with any chunks that neighbor them. Oh, that's where I had that theory stuck in my head of like merging free neighbors. Oh, that's funny. So that was the point I just made. So it's talking here, because that requires a memory allocator, blah, blah, blah. So you have to implement the list inside the memory region that holds the allocations. It can be done many ways, but the easiest is for chunks to add a small section of memory before the memory intended to be used by the calling code, and storing whether the chunk is free or allocated its size, including the header, so we can reach the next chunk. And so it's all about the metadata cost. It's something you've got to think about, like where is it going to live? How are you storing that? How are you searching it? You can get fancy about this. Some free lists use a single link list that kept sorted, so previous orders behind the next stored ahead of memory. Yeah, I think we need to start simple. I think we need to just do a really crappy bump allocator. So the bump allocator is the fastest allocator there is. All it does is give you a pointer to where it currently is and advances a pointer by the requested size. Super simple. It can't free memory, however. Oh, hold on a minute. If you did that, um, I have just had a thought about a problem that I already have with my physical memory manager. Let me just go quickly check my log. Beginning to wonder now if bitmap allocating. Let me just check this code. I've got a feeling I've got a bug. Get address from page. Um, so as I'm iterating through the memory map and I find a usable memory map region, I'm tracking the total bytes, the maximum pages available plus equals that length and page size, and the highest address. Oh no, it's not a bug. Right. I'm treating the entire memory region as a linear bucket of space, and what I'm doing is marking places in RAM that are not free. So what I have to remember yeah, so I solve there's a problem even in the physical world of memory where it's a bit fragmented because there are some parts of RAM that are reserved for memory maps and the kernel and all sorts of stuff. So if you get to the end of one of the chunks and you happen to need to allocate the next page, you can't just assume there's a page next door to you that's available. You may hit one of these boundaries where actually your next free page is much further on in RAM and you're no longer continuous. And what this logic here is doing, it's checking for that limitation, like it's doing this bounds check. And it's looking for a block big enough for you. That's right. And then on that allocation metadata, I'm just storing where you began your allocation in the map and how many pages you got allocated. Which is enough then to understand the size of the allocation, the start and the end, blah, blah, blah. But will that, so knowing that's the way the physical memory manager works in Pages, will that be a problem when we start allocating for a bump allocator? And I think the question answers itself because the problem has been solved in the physical memory manager. So if your bump allocator says, yo, give me 4 pages of memory, the physical memory manager will make sure you get a continuous 4-page allocation if you hit the boundary of a reserved space in RAM. And that's fine. So let's think about that forward-only bump allocator. You've got a pointer to your next available space in RAM. And there's a current limit to what you have allocated. So let's just pretend you've got 1 page allocated. You've got 0 to 495 bytes in RAM. And that pointer begins its life at 0, and you ask for 4 bytes, okay, that moves to +4. You ask for another 4 bytes, it moves to +8. Eventually, ... you're going to get to the limit of 4095, and that's when it's going to start then asking for a kalloc. Give me a page, please. '8192. Sorry, I had to check that. So now we own 8192. I've got to be careful though, because that page that we just got back there is not continuous to that page in RAM in terms of its location. Does that matter? When I perform another +4 allocation here, we're getting back a memory address, right? In that new page. But I guess what you can't do is you can't use partially 2 bytes from this page and then 2 bytes in the new page. You can't cross the boundary. So you would have to just go forward and go, oh, we've got a new page, and you don't fit in the first page's remainder, so let's just forward the pointer onto the new page, and now you're getting 4 bytes from the new page. And how would I track that? I guess just the page, the memory location, right? Yeah, it's just a memory location of that allocated memory. Like I would know it was in that page and not this page. I guess as I allocate the pages and store them, we can just store the address of the page. And then there's a quick lookup on knowing if something's being allocated in what page. So the bump is kind of like dumb and simple. It's a forward-only allocator, which is kind of like, okay, we can do that. That's hello world, your cowboy allocator. But if I, in my own mind, wanted to add a 3 to this, and I started freeing up some of the areas in that page that I was allocating, in the bump allocator, I've now got holes. And what would happen in this kind of location here, if somebody asked for another 4 bytes, but this one became free, the allocator needs to realize that the first 4 bytes are now free. So the bump cursor can't just be forward only anymore. It needs to kind of like rewind and check for that fit earlier on in the page. And this is where the time to allocate is increasing. There's a cost to the allocation because you're now searching. Your forward only is really simple. You're like, yeah, I've got that space, allocate, return. Worst case is I haven't got the space, grab a new page, allocate, return. We're now going towards let's look for a place for my allocation. Oh, I found somewhere. Now I can do the allocation, but that search is going to be costly because I'm going to keep walking the metadata looking for a space. And I guess this is kind of why you have 3 lists. One that represents small objects, medium, and large. Because your search would be quicker if they were segregated. I don't even want to think about that for now, though. That's confusing the matters very quickly. Well, so as soon as you step into the arena of doing a free implementation, you are up in the complexity quite quickly. Linuxism name. Oh, here's another search term I can do. Simple list of blocks. I think these are all just Linux. Yeah, these are all Linux references again. Same there. Here's a link on the university page. Oh, that's funny. So here's a presentation slide, and as I was just thinking about the allocation in the bump one, that they're acknowledging you could have a split allocation when you go to a new page. It's good to see someone else is kind of like recognizing that problem. Split a 512 block chunk into two 250 block chunks. Try again. We want a 64 block allocation, none available. Any 128 block chunks to split? No. Any 256 block chunks to split? Yes. So this is the buddy example, which is not, again, I don't think we can find here's another PDF. Oh, this might work. Page frame manager, which we've got dynamic memory allocator. Right, this is talking about user space and kernel level allocators, which is whatever. Bump allocator, malloc 6, malloc 12, malloc 20, malloc 5. That's a forward only thingy. You can't free memory. It's a fragmenting solution. Yeah, it's pretty shitty. Keeping per region metadata. Prepend the metadata to the object as a header. On malloc size, look for free object of size or at least size plus size of header. Yep, you could do that. Tracking free regions. Link the free objects in a linked list using the next in the free object header. Keep it in the list in the header and global variable. Performance issues. Again, what I was just thinking about, allocation, quickly find a big enough object. Searching free lists can take time. Or can avoid searching altogether by having pools of same size objects. And that was about having no separate linked lists. But that feels scary because they're overlapping. Or they would have to overlap. Maybe. Concurrency issues need locking for a concurrent malloc and free. True. If locks are used, only one thread can allocate and deallocate at any point in time. Lock on lock is pure overhead, even when uncontended. True. Per thread heaps. Oh, right. Yeah. Now they don't have to lock. I'm glad we came across this PowerPoint. This is pretty handy. Hoard, a scalable memory allocator. Let's put these good ideas to work. Superblock. Allocate a heap for each processor and one global heap. Not threads, but CPUs. Requires some way to figure out the current processor. No such mechanism on x86. What? Yes, there is. Um, yeah, this has gone up way above what we need to think about already. I think what I'll try just to get me going is the bump algorithm, even though it doesn't have a free implementation. I'm not too bothered that it doesn't, but so I don't know how this slots into virtual memory page entries though. That's my other discussion that I need to have in Discord. Is regardless of the allocator. So this sits aside from virtual memory. So you've got the physical memory manager that is used by the bump allocator. And the bump allocator is like, okay, I'm your malloc and you're free, okay? And now it takes care of giving you the malloc address, and it's like, here's your address, there's your memory. But then how do you register that in virtual memory? Is it actually, is it directly aligned with the bump allocator? Because the bump allocator itself knows about the pages that you're allocating. So it's as it's allocating those pages, it could map those. Like it could just call the VM at the point it's allocated a page and says, map me this page. And it registers a new entry. Um, um, God, there's going to be such interesting problems. Um, so, as an example, is what if somebody calls malloc with the value of 10,000? Give me 10,000 bytes, please. I'm going to load some data from a file and I need to dump it somewhere in RAM. So then, okay, what does the PM respond with? It's like, yeah, here's 3 pages. And then what does the virtual memory manager do? It goes and registers and maps 3 pages for you. I guess so, right? It would. Because they've got to be mapped. Or you can't have a memory address. So they do get mapped in the virtual manager. Those 3 new pages from the PM have now been mapped in the VM. And you have addresses and offsets into those pages. And everybody's happy. I guess a problem that I need to solve is how do I get a page in the virtual memory layout? Like, where's it going? What's the strategy of starting at the 4th level? Am I just looking for the first non-present entry? And then it's like, bam, I've got one. Okay, I'll use it. And then I'll just assume the next pages underneath that guy are also not present. And I can just activate all of the entries going down the tree and go, there we go, we've got a page. But then when I go to allocate the second page in the VM, I kind of want to walk down the tree and get to the last level and activate the next node in the last level. Oh man, this gets complicated. This is why I need to take it slow. I need to kind of implement these parts really slowly so I can see the problems that come out of them and understand what the algorithms are there to solve them. Now, question, if we were going to write we were going to write the bump allocator. It's just an array of max pages available. The maximum number of pages available in RAM across the entire memory map. So I could just create an array of, would it be an array? Would it be bits? A bitmap. Would it be a bitmap or would I need more metadata? Let's think about that for a second. The problem occurs when you ask for an allocation. No, you want start and size. Yeah, you do. So we could have a uint64 for the start page number, because why limit ourselves? Let me just try and map this out in my head. Would have its address. I guess we would have its size. In what though? Bytes? Size in bytes. So that becomes a list that what do we call this? I mean, it's metadata. You just call it bump map for now. Is that too much metadata or not enough? We'll find out. I've got a feeling at the beginning we'll have too much, and then I'll be able to think about reducing it. So this can be a static map page is available. So there's just a constant cost of the metadata on boot to initialize the bump allocator. I can live with that too. That's fine. It's not going to be a lot of room. It will be though if a lot of bits. A lot of bits of metadata. Let me just have, gosh, we've really filled our brains up with a lot of domain words tonight. So our world is opening up, if anything. I just want to read up on a first fit allocator. Oh man. Okay. I think this is what we've already got in our physical memory manager. Kind of, and kind of not. Is there a Wikipedia on this at all? Somebody's implementation. Yes, I could think about using a linked list. As soon as I step into the realm of using a linked list, I'm opening the door of being able to defrag my space because I can check neighboring nodes on deallocations. Sounds like it's going to be a fun problem domain. We've probably got a few weeks of effort to spend here. So my desire of being able to write a disk driver is slipping away slowly. But yeah, there's an interesting mountain that we've come across here, and I think we're going to traverse it for sure. It would be nice to get to a point where I'm going to be like comfortable allocating and deallocating specific minute byte requests. How did you plan on doing disks? So we started with writing the NVMe driver. And now I could take a sidestep and just do this straight away, but because I thought that I needed virtual memory to do this, but apparently I don't need it at all. I can just control the NVMe controller without using any virtual memory setup. So I could come back to the NVMe controller and start writing a file system and talking to the hard drive. But I guess I feel like I need to get a handle on how paging works and how even a simple allocator works, because at some point we're going to want to write user programs, right? And we're going to want to give a user program like its own heap and its own virtual memory setup. And all of that needs this. So it's all like core domain knowledge that I need, so I don't mind. There's going to be as much fun writing the driver for disk access and then doing FAT32 or something like that. As much fun as doing the memory allocators. What's fun about the memory allocators too is that we can write performance tests and, you know, unit test them quite easily. Also doing SATA 3. I don't know, I could, I guess. I was just told to do NVMe to begin with, like not even IDE or anything like that. It's just an old tech that's not used anymore. So NVMe was the one to go with. Still a pile of spinny things around, yeah. By the time I do anything with this OS, I'm probably not going to have spinny things around on my desk. Honestly, I don't even know if this project's ever going to leave QMU. Wouldn't it be crazy if I did try to run it on a proper x86 CPU, though? I'd probably have a ton of bugs. I mean, naturally, right? Because it's not QMU. So I'm going to be put on a real world chip with a different setup and different config and different addresses and I remember when I did the LAPIC, there was some assumptions I did about QMU in here. Or it could have been the IO APIC. I can't remember. Oh no, it was the ACPI. Yeah, this is like the database of the PCI bus and stuff. Those in-memory tables of things. Um, 3 hours. Right, yeah, I'm kind of like, it's 1 a.m. here, so I'm gonna have to get going now. But oh boy, have we got our work set out for us, which is great. So we've got some algorithms to learn. We're going to learn about how we're going to structure this bump allocator. So we're going to get challenged on, being minimal and efficient with our metadata. And it'll be fun trying to plug things into the virtual memory manager too. Like that's going to be an interesting push because currently we can't allocate in the VM. We can walk addresses, but actually creating new addresses based on a physical address that we get from the PM, and then generating a virtual address from an entry in the page tables is something we've yet to do. I don't think it's going to be too bad. Like, again, we can just slot in a cowboy algorithm that just says, go find the first non present table, and then off you go allocating. So we can get past this too quite quickly, which would be cool. And then hopefully I can sleep on all of this knowledge of how all of these things are going to clip together. So, yeah, lots of fun stuff to do now. And it's exciting. I like this. I like knowing that we have work to do. But yeah, thanks for watching, and I will definitely be on tomorrow. Tomorrow is a nice, relaxing day, and I'm excited to come back to this. So I'll definitely turn the stream on, and we'll get back to we'll start coding all of the things we were talking about tonight. So we'll do the bump allocator, we'll do the creating a VM entry. It's going to be really fun. So I'll be back around the same time tomorrow night, maybe a bit earlier. Do it a bit of a longer stream. But yeah, thanks for watching, guys, and thank you again, Leia, so much for the subs, the gift subs to the OG viewers. That's very nice of you. But yeah, this whole stream will it will be exported onto YouTube if you guys ever want to rewatch it. So yeah, have a great night, and I will see you tomorrow.